Today we're going to be discussing slope. Last time we went over how to graph a line by plotting some points, but this time we're going to go over how to more systematically plot a line directly getting information from its equation. But before we can directly get that information from its equation, one of the key pieces of information that you want to get from an equation is always the slope of a line. In essence, a slope is just somehow measuring the steepness of a line. It's also known as a rate of change. And this is actually an extremely powerful concept. Really, actually, Calculus 1 is basically studying fancy slope. This is a concept that comes up all the time in mathematics because you often want to know how are things changing, how fast are things changing. That's what slope really tells you. In terms of how do you find slope, there's a couple different ways to think about it. If you physically have 2 points on a grid, you can just physically actually count, making sure that you're keeping the units straight that are labeled on your graph. The rise, change in y, divided by the run, the change in x. You also just mathematically, if given 2 points, let's say this point up here was, 5, 3. And this point down here was, let's say, -2, -7. Then rather than counting physically up from -7 to 3, you could say, okay, well, the distance between 3 and -7 would be 3 minus -7. The distance between 5 and -2 would be 5 minus -2. And you would get that this would then be 10/7, that you rose 10 units and you ran 7 units. That would be another way to think about it as well. Oftentimes, being able to be comfortable with the formula to just be able to plug and chug any 2 points is going to be a little bit more consistent, particularly whenever the numbers become just literally too big to physically count on a graph. But the idea is it still is what you're doing is change in y divided by change in x. Now, slopes also do have a sign that depicts what direction that rate of change is going. So in a way you could think about this as sort of reading left to right, sort of picturing somebody walking on top of the line from left to right. And if from left to right on top of the line you're going uphill, that is a positive slope. So whenever it comes to just measuring rise over run, between the 2 points you would be going up, so going in the positive direction, and you would be going right, which is also the positive direction. So when you do rise over run, you end up with a positive over a positive number. Or alternatively, if you were sort of to count the backwards way, then you would end up with a negative over a negative. Either way, you're going to end up simplifying to a positive slope. Versus for a negative slope, if you're still going from left to right on top of the line, you're now going downhill. So that's considered a negative slope. If you were to count the rise over run between 2 points, you'd either be going up and left, so you'd be going positive direction and then negative direction between the 2 points, positive divided by a negative being a negative, or you could be thinking, well, I'm going down and right, which would be a negative divided by a positive. Either way, that would simplify to a negative number, so that would be downhill. So we say positive slope uphill is also known as anything that is increasing, versus a negative slope downhill is also known as decreasing. And again, we interpret increasing, decreasing as looking at that line going from left to right. Zero slope is where everything is constant, where there is no change. So you always stay at the same y over the x is changing as much as you want. So if you were to plug into the equation, you'd end up with 0 divided by some number, no matter which points you count in between. And 0 divided by anything is just 0. So that would be a 0 slope if it's a straight across line. Versus an undefined slope is straight up and down. Between any 2 points, the y's change as much as you want, but the x's never change. So when you plug into the equation, you end up with a number divided by 0, which is undefined, aka does not exist. The way that I oftentimes will also remember it is that this physically sort of looks like an I for infinity, if you want to remember it that way as well. So let's practice this a little bit. So I'm going to encourage you to pause your video and either by formally finding the slope or just plotting them, figure out what type of slope goes through a line that would connect each of these sets of points. So for the first set of points, we got -2, 1, and then 2, 5. If we connect those points, we see that from left to right, we're going uphill. So this would be a positive slope. We could find out exactly what is the slope similarly by actually seeing that we rose 1, 2, 3, 4. We ran 1, 2, 3, 4. 4 divided by 4 gives us 1, so it is a positive slope of 1. Alternatively, if you were to formally plug into y2 minus y1 over x2 minus x1, you would get, you have to kind of just arbitrarily label one of them to be first, one of them to be second. I'm just going to go ahead and label the first point x1, y1, the second point x2, y2. It doesn't technically matter as long as you're consistent. So then you would end up with 5 minus 1 over 2 minus -2 to get you 4 over 4, which is 1. I'm not going to formally find the slope for the rest of them. We're just going to kind of see if they're positive or negative because we're going to have plenty of time to formally find the slope later, but just wanted to kind of give you that preview there. For this next one, if we were to plot 3, 4 and then -1, 4 and connect these points, well, now that's a constant. A straight across line has a slope of 0. Again, if you were to also formally plug it in, then you would get change in y over change in x. You would get 0 over a number, which is just 0. Another way to confirm it. For this next one, if you were to plot these points, so 0, -2, and then 0, 3, connect those. That is a straight up and down line, so whenever it's a straight vertical line, that is an undefined slope. And again, or say does not exist, something along those lines. And again, you always can formally plug into the equation to confirm, because if you were to do change in y over change in x, you would end up with a number divided by 0, and that is not allowed. That would be does not exist. And last but not least, these last 2 points, if you were to plot -3, 5, and 1, 1, and then connect those points from left to right on top of the line, that's going downhill, so that would definitely be a negative slope. And just, I lied before, I said I wouldn't formally find the slope for these, and we might as well. So here our rise is 1, 2, 3, 4. Our run is 1, 2, 3, 4. So we end up with 4 over -4, or -4 over 4, whichever way you want to think of it, because we went down 4 and right 4, or you can think we went up 4 and left 4. Either way, because you also could have drawn this triangle the other direction, right? Either way, it's going to be mixed signs, so you end up with a slope of -1 this time instead. Or if you were to formally plug into the equation, you would get 1 minus 5 over 1 minus -3 to get you -4 over 4. So in order to find slope from the graph, you're going to do kind of that process I was just modeling earlier, where you need to pick 2 clear points on the line. Be careful that you should not be estimating any coordinates. So on sort of the lines we were looking at before, I don't know why you would try to do this, but you can't like do -1.5, 3.5 type of deal. Don't actually try to estimate it. If you try to estimate it and it doesn't fall clearly on those grid marks, chances are you're going to maybe estimate wrong and you're going to end up with the wrong points. Then you want to count how many units you go, and you want to be careful about how they're labeled. Sometimes they count by ones, sometimes they're counting by twos or by halves or something like that, so you want to make sure you're counting in the same way that your tick marks on your graph are labeled. If you're going up and down, that's the rise, left or right, that's the run, and then you need to visually decide if it's a positive slope, negative slope, zero slope, or an undefined slope. And then simplify as necessary as well. So go ahead and pause your video and try to find these slopes yourself before we go through it. So for these, you could have picked whatever points were clearly on the line for you. For me, that y-intercept of 0, 1 seems pretty clear. And then also this point over here of 5, 4 seems pretty clear. So that means our rise is 1, 2, 3. 1, 2, 3, and then our run is 1, 2, 3, 4, 5. So this would be 3 over 5, or if you were to formally plug into the equation, y2 minus y1 over x2 minus x1, I'm going to arbitrarily call this one my x1, y1, call this one my x2, y2. So that would be 1 minus 4 over 0 minus 5. 1 minus 4 gets you negative 3, 0 minus 5 gets you negative 5, negative divided by negative simplifies to a positive divided by positive. That would be another more formal way of doing it as well. So you can either count or you can actually plug into the equation. Let's check out another one. So here it looks like that y-intercept is also nice and clear, so I'm going to use 0, 10. And then it looks like a next clear point here is 2, 6. So this is a good example of where it's actually not counting by ones, so you want to be a little bit careful. Here we go up to 4 because remember we're counting by 2s, so the rise is 4 over the run in this case is 2 to get you a total slope of 2 because that's how it simplifies. Now had you not noticed that, in this case it actually would have still simplified the same because both the x and y axis are at least scaled by the same thing, but if they weren't, then that's a place that you could get messed up. And then again, if I were to sort of plug into the equation instead, x2 minus x1, then I could be doing 6 minus 10 over 2 minus 0 here, and then we end up with negative 4 over 2 to get us negative 2. Now, we got a negative, and is that what we should have noticed before as well? Yes, absolutely. How do we know he's negative? Because from left to right, he's going downhill. Before, in the first example, this was going uphill, so this slope is positive. Here in this example, we're going downhill, so this slope is negative. So be very, very careful. That slope was actually a negative 2. So this is a good example where, you know, it's also kind of helpful to formally plug it in to kind of double check yourself on those signs as well. But this is definitely going downhill, so he's definitely negative. For this last one, this is a straight horizontal line. So that's going to be considered a slope of 0. Now, could you also formally pick some points to double check? Sure. So I'm going to pick the points, looks like 1, 1, 2, negative 3, and then we've got the point 3, negative 3. So for these, our rise was 0, our run was 2, which does indeed simplify to 0. Or we could formally plug in negative 3 minus negative 3 over 3 minus 1. Negative 3 minus negative 3 gets us 0. 3 minus 1 gets us 2. And that does indeed simplify to 0. So we are good. And you can always just sort of rely on the formula as well, kind of straightforwardly. And if you're going to be relying on the formula, I always encourage you to go ahead and pick who you're going to choose to make x1, y1, and who you're going to choose to make x2, y2. And if you had subtracted in the other order, as long as you were consistent, you would have still gotten the same thing. The only thing that would have been different in this case is you would have gotten negative 18 over negative 4, and then you would notice that that would have simplified to a negative divided by negative as a positive. But let's take a look at some examples of that. So in particular, if we have the points negative 3, 1, 2, 3, up 1, 2, and the points 1, 6. Visually, we're expecting this slope to be positive, and then if we were to actually plug into the formula of change in y over change in x, we can go ahead and label x1, y1, x2, y2, doesn't matter which one you label which. 6 minus 2 over 1 minus negative 3. 6 minus 2 is 4. 1 minus negative 3 also gets us 4 for a final slope of 1. It also does look like on our grid that we're going up 1 over 1, up 1 over 1, kind of in between these 2 points. But you also could have counted 1, 2, 3, 4, run 1, 2, 3, 4, and that would have worked as well. And in particular, we can use the formula to go ahead and just find the slope even whenever we don't have the visual to necessarily check. What I would still encourage you to do is you sort of sketch out to the side approximately where stuff is. So you would expect negative 2 to be somewhere around there. And then you would expect 4, negative 5 to be somewhere around here. So I would expect my slope to be negative at the end if I'm going to do this correctly. So let's go ahead and actually plug in. So I'm going to actually arbitrarily label this the other way around this time. We'll call this x2, y2. x1, y1. That means we'd be doing negative 5 minus negative 2 over 4 minus negative 2. Now I'm a little bit paranoid if I did that straight the other time. Yes, I did actually follow what I labeled. Okay. Negative 5 minus negative 2 gets us negative 3, because that's the same thing as negative 5 plus a positive 2 whenever we're subtracting a negative. Similarly, 4 minus negative 2, same thing as adding a positive. That is going to get us 6. And then negative 3 over 6, both of those are divisible by 3 to get us negative 1/2 as our final slope. We also could find missing information using the formula. So a problem like this is somewhere where you definitely want to be using the formula, that we know that slope is equal to y2 minus y1 over x2 minus x1. In this case, they gave us the slope was negative 1/3. And then I'm just going to kind of arbitrarily label. I'm going to choose to make this one x2, y2, and I'm going to make this one x1, y1. So y2 was given as 10. y1 is what we don't have. x2 was given as negative 2. x1 is 4. And then I want to go ahead and start to simplify this using knowledge of how to solve equations. So in particular, I notice that this denominator can be simplified a little further. So I'll have negative 1/3 is equal to 10 minus y1 over negative 6. Then I want to kind of clear my denominators, and it looks like my least common denominator in this case is negative 6. And I'm also on this left-hand side going to assign that negative either to my numerator or denominator. I'm going to choose to assign it to the denominator. Doesn't really matter which one, but you just need to make sure that you're kind of keeping straight that there's not a double negative going on there. So I'm going to multiply both sides by negative 6. Negative 6 divided by negative 6 cancels to make 1. Negative 6 divided by negative 3 is going to go ahead and make a positive 2. I'm going to go ahead and continue this up here just so that if you're reading the notes later, it sort of flows on the same page there. So then we get 2 is equal to 10 minus y1. My goal is to get y1 by itself, so I'm going to go ahead and subtract 10 from both sides. 2 minus 10 gets us negative 8, equals a negative y1. y1's being secretly multiplied by negative 1 right now, so I'm going to divide both sides by negative 1. And then I will get positive 8 is equal to y1. So that final coordinate is 4, 8, with 8 being that missing piece. Then I would encourage you to go ahead and double check yourself. So double check, well, if I actually plug this back into the slope formula, do I get what I expected? So the slope for between 4, 8 and negative 2, 10. If I'm going to go ahead and label x1, y1, x2, y2, 10 minus 8 over negative 2 minus 4. 10 minus 8 is going to get us 2. Negative 2 minus 4 gets us negative 6. 2 divided by negative 6, both of those are divisible by 2 to end up with 1 over negative 3. That is negative 1/3. We know we did the problem correctly.